Next, we're going to talk about graph isomorphisms, and this gives us a way to determine or describe the fact that two graphs are essentially the same as each other, just that maybe one has the vertices labeled differently from the other, and maybe we're calling the edges something different. So two simple graphs. So for this definition, we're looking at undirected graphs. G1 with vertex at V1, edge set E1, and G2 with vertex at V2, edge set E2 are said to be isomorphic if and only if there's a bijection F from V1 to V2, such that A and B being adjacent in V1 is equivalent to F of A and F of B being adjacent in V2. So we're going to take vertices that are adjacent and map them to adjacent vertices in the second graph. So looking here, these two graphs look like they might be the same. If I were to take this vertex 3 in the second one and sort of pull it up here, take vertex 2, pull it down here, then it would look basically the same as the first graph. I'll go ahead and label these. This will be our G1 and our G2. And if they are isomorphic, it doesn't matter which direction we set up this bijection. It can go from the first vertex set to the second, or the second back to the first. If there's a bijection, it's going to be invertible, and so we could set up the mapping in either order. So here, if I'm going to actually go through and define the isomorphism, keeping in mind what we just described, if I take vertices 2 and 3 and drag them around so that they change positions, then we're going to have this square arrangement. Or if I take C and B and interchange their positions, again, keeping the same edge connections. So with this one, we'll take F of A, say that that's equal to 1. So I'm just going to go through and write out the function values for each of the vertices in my first graph. So A is going to be equal to 1, or A is going to get associated with 1. And then B, I can't map B to 2 because A and B are adjacent in G1, but vertices 1 and 2 are not adjacent in G2. So I need to map B either to 3, that's adjacent to 1, or I could map it to 4, but I need to map B to something that's adjacent to 1, so either 3 or 4. I'll go ahead and use 3. And then from there, B is adjacent to C, if I'm moving on to C next. So that means that I'm going to have to map C to something that's adjacent to 3. And I've already used up 1. I can't use that as an output on another, so I'm forced to make that 2. And then finally, when I get over here to D, D is adjacent to both A and C. So whatever I map D to should also be adjacent to 1, because I mapped A to 1. It also needs to be adjacent to 2, because I mapped C to 2. And the only thing that's left here is going to be 4. If there's going to be a bijection, it needs to be 1 to 1 and onto. And because of that, if I have two graphs with different numbers of vertices, then we know automatically that they're not going to be isomorphic to each other. So generally, you'll probably only be asked about isomorphism in contexts where it's maybe not quite that immediately obvious that they aren't. Now, showing that two graphs are isomorphic in general can be kind of tricky because we would have to go through and check all of the possible pairs. So looking at all of the edges in the first graph, and then check what they map to, make sure that that corresponds to edges in the second graph. So there's going to be a lot that we have to check there, making sure that we maintain the adjacencies in the way that we're supposed to. So looking at something like 5, thinking about the isomorphism, the bijection that we're setting up, because we're talking about adjacent vertices, then the degrees are going to have to be the same. I can't take something with degree 1 and map it to something with degree 2, because that degree 2 vertex, again, is going to have multiple vertices adjacent with it, whereas the degree 1 is just going to have one other vertex. And so I'm not going to be able to maintain this definition if I'm mapping a vertex of a particular degree in one graph to something with a different degree in the other graph. So that's actually one way that we can determine whether or not two graphs are non-isomorphic. We can go ahead and write out the degrees in each one. So I could do just say degree list. Doesn't matter the order that we go in. Looking at each of the degrees in G1, I've got degree 2 for A, degree 2 for B, degree 2 for C, and also for D. If I write out the degrees in G, I've got a degree 1, and then a degree 2, another degree 2, and then a degree 1. Again, the order I'm writing those down in doesn't really matter. But the important thing here is that we have these two degree 1 vertices in G2, but we don't have any degree 1 vertices in G1. So that tells us that these two graphs cannot be isomorphic to each other. So non-isomorphic, I can't set up the bijection in a way that's going to preserve the adjacencies, because I'm going to be forced to map something in G1 to a vertex in G2 that's not going to be adjacent to the appropriate things. So showing that two graphs are non-isomorphic, we can look at properties in one of the graphs that would be what's called preserved under isomorphisms. These are called graph invariants, something that we have in one of the graphs that doesn't show up in the other. So we can look at things like the number of vertices. If I don't have the same number of vertices, I'm not going to be able to set up a bijection. We can look at the number of edges. Again, if we don't have the same number of edges in both, then I'm not going to be able to set up the bijection in a way that preserves the adjacency that we want. Looking at vertices with particular degrees, I need the same number of each degree. Now that just by itself isn't enough, as we'll see with some of our later examples. We can also look at subgraphs that have certain properties. We can also look at what are called simple circuits of length 3 or greater, and we'll illustrate that here. So as we're looking at these two, intuitively, just based on the shapes, these don't look like they're going to behave in the same way, but we can identify certain problem areas. There are going to be several things that we can do here. So I could look at degrees. I can write out the degree list on each. In G1, we have degree 2 vertices all the way down. In G2, we've got a degree 1 vertex. We've got a degree 2 vertex, another one over here, and then we've got a degree 3 vertex. So that tells us right there that they're not going to be isomorphic. If we were to look at, say, the number of edges in both, these each have 4 edges, so that's going to be inconclusive. If they do share a property, then there may be another one that doesn't work out. So same number of vertices, same number of edges, but we didn't have the same number of vertices of a particular degree. Looking at subgraphs with a particular property, if you were to look at all of the, say, degree 2 vertices and form that subgraph, and we'll keep all of the edges that we had in the original one. So with G1, I'm just going to end up with G1 again, since they're all degree 2. But if we draw the subgraph with all the degree 2 vertices and their adjacent edges in the second one, then we end up with this. So that will highlight an area where the bijection that we're trying to define isn't going to satisfy the properties for an isomorphism. We're not going to have the correct adjacencies. If we were to look at the subgraph of all of the degree, say, 3 vertices, that would be even easier here. I would have just the vertex 1 in G2, and I would have an empty graph, empty subgraph of G1 for that. Same thing with all the degree 1 vertices. I'd have just the vertex 2 from G2. I wouldn't have anything from G1. The existence of a simple circuit of a particular length, and by a circuit, and this needs to be greater than or equal to 3, as we mentioned there, but I can start at one vertex, travel through the graph without repeating any edges, and end up back at that same vertex. So that is going to be the length of our circuit. We have a simple circuit, again, no repeats, of length 3 in this case, but there are no length 3 simple circuits in the first graph. If I start at any of the vertices, I'm going to have to go through 4 edges before I'm back where I started. There's no other way around that. So we have a simple circuit of length 3, but our first graph has no simple circuit of length 3. If there were, that would give us one way of properly associating vertices in one graph with the other. I could simply travel around the circuit in both of them and assign the pairs of vertices as we come to them. Be one way to create the isomorphism, again, if there is one. Let's look at another example. In this one, we can see that we've got 8 vertices in each, so that's not going to give us a way to say that they're non-isomorphic. If we look at the number of edges, we can see that we have 10 edges in each of them, so that property isn't where it would break down if they are non-isomorphic. And if we go through and list out the degrees, again, I'm going to call this G1, call this G2. Put that off to the side here. And I'll check these off as we go. So we've got a degree 2 there. B is a degree 3. Another degree 2. Degree 3. And then we've got 2 more degree 2s and 2 degree 3s. Whatever order we want to go around those in. And if we look at our second graph here, we've got a degree 2 and a degree 3. I'll write these out in an order that kind of matches these up. I've got a degree 2 over here, and I've got a degree 3, and then we've got a degree 2, a degree 3, a degree 2 right here, and another degree 3 right here. So looking at those, we have 4 of each degree, 4 degree 2 and 4 degree 3s, and that happens in both of them. So that also doesn't give us a way to show that they're not isomorphic to each other. But if we look at the subgraphs of all of the, say, degree 3 vertices, or of all of the degree 2 vertices, so subgraph of all the vertices that have a particular property. That's another way that we can try to identify differences. So in the first one, all of the degree 3 vertices, that's going to mean D and H and F and B. And the names don't matter so much. Let me just draw out the subgraphs that we get here. I'll try to keep the same sort of relative ordering. Go ahead and label these just so we can see where they came from. If I do the same thing over here, all of the degree 3 vertices, that's going to be S and W, Z, and V. And we see that the degree 3 vertices, there's a cycle of length 4 that contains all of them. I don't have that cycle of length 4 showing up in the first graph. So that is enough to tell us that they are non-isomorphic. If we start trying to map vertices to each other in such a way that we're maintaining the connections, we're going to start to run into issues. I could say F is going to map to S, B is going to map to W, but then W will need to be adjacent to another degree 3 vertex, and I don't have anything else that B is adjacent to that's degree 3. So it would break down there. If we look at all the degree 2 vertices, that should also show us that they're not isomorphic to each other. In the first graph, we've got A, E, G, and C. And then in the second one, we've got X and Y, and T and U. Like that. And again, if we try to set up the isomorphism, we've got this degree 2 vertex X being adjacent to a degree 2 vertex Y, but I'm not going to be able to do that in the first graph. So those would also show us, those two subgraphs show us that these are non-isomorphic. Looking at a couple more examples. In this one, we can see that we have all degree 2 vertices. We've got the same number in both. Each of them have 7, just going through the index values. So looking at any subgraphs, that's not going to help me. I've got the same number of edges here as well. So it seems like these should be isomorphic to each other, and we could think of sort of pulling the vertices in the second graph around, or pulling the vertices in the first graph around to make it look like the other one. If I want to know how I'm supposed to map these, so we'll go ahead and define our function values and write that out. To maintain the adjacencies that we want, we can have the isomorphism going between in either direction. So for this one, I'll have it going back that way. Again, it's a bijection, so there will be an inverse, just reverse all of these definitions. When we're writing these out, we're going to just list out each vertex and its associated vertex in the other graph. V5, 6, and 7. So to have these mapped out in such a way that we maintain the adjacencies that we want, so whatever V1 gets mapped to, I'm going to need it to be adjacent to the thing that V3 is mapped to. So let's start highlighting this as we go. So I'm going to think of going from, all right, V1 to V3. I want those to be adjacent. And so if I start over here, it doesn't really matter which one I pick. Let's say I start with, I don't know, U3. Let's say V1, I'm going to make that equal to U3. That's fine. But then I'm going to follow U3 around. Again, it doesn't matter where I go from there. Let's go on to U4. So that tells us that since V1 and V3 are adjacent over here, then if I'm going to map V1 to U3, then I'm going to have to map U4 to something that's adjacent to, or sorry, I'm going to have to map V3 to something that's adjacent to U3. So if I'm moving this way, U4, or if I go the other way, U2. So those are the only two options then for the V3 function value. So I'll fill that one in next. Again, if I'm continuing in that direction, we'll make that U4. And then following the next edge along, so V3 down to V5. And now I only have one option. U4, follow that along down to U5. So V5 and U5 are going to be associated with each other. And then continuing along, so V5 is then adjacent to V7 along that edge. And that means that the thing that I mapped V5 to, which was U5, needs to be adjacent to the thing that I map V7 to. So I'm going to use V6 as my U6 as my V7 function value. So V7 maps to U6, and we'll just continue following that cycle along. Now, in this case, all of the edges form a cycle, so I'm not going to have any other pieces that I have to deal with, any other components. It's a connected graph, so I can just follow that cycle around and be able to map out my entire isomorphism here. So V7 adjacent to V2, and so over here we're going to go from U6 up to U7. So V2, I'm going to map that to U7, and then V2 is adjacent to V4. U7 adjacent to U1. So V4 will get assigned to U1, and then V4 adjacent to V6. U1 is adjacent to U2, so that means that V6 and U2 are going to be mapped, paired up together. And then if I follow the last edge around back to where we started, so V1 and V6 are adjacent. And so whatever I mapped V6 to, which was our U2 value here, should be adjacent to what we mapped V1 to. V1 got mapped to U3, and that does work. That's that last edge that we're looking at there. So that checks out, means these are isomorphic, and there's our isomorphism. In the next example, go through and look at properties. Let's just talk through these. So if I'm starting to think about the number of vertices, or the number of edges? Well, we can see that these all have the same number of vertices, same number of edges. Looking at the degrees, I've got some degree 1 vertices. I've got 1, 2, 3, 4 of them in the first graph. I've got 1, 2, 3, 4 degree 1 vertices in the second graph. So that doesn't help. I've got some degree 2 vertices. I've got one here and one here. And then we've got a degree 2 vertex and another degree 2 vertex. So that matches up. U3 and U6 are both degree 3, but V2 and V6 are also degree 3. So the values of the degrees, or the degree lists, would look the same if I order them appropriately. So we could look at subgraphs next with particular properties. So for instance, if I look at all of the, say, degree 3 subgraphs. Well, here I would have U3 and U6. Those aren't adjacent over here, so I'm not going to have anything between it. And comparing that to V2 and V6, well, those look the same. So that doesn't tell me that they're non-isomorphic. So we'll try something else. Maybe if I look at the degree 1 subgraphs. So in that case, I'd have U1, U4, U7, and U8. No edges between them, because none of those are connected. But if I look at the degree 1 subgraphs over here in V, so comparing that to V1, V3, V7, and V8 over here, well, those look the same. So that doesn't help us. But if we look at the degree 2 subgraphs, finally get what we're looking for in terms of a difference. So U2 and U5 are the degree 2 over here in the first one. Then in the second one, we've got V4 and V5 as the degree 2 vertices, and those are adjacent to each other. So as we are mapping our vertices out, if we're trying to form an isomorphism, get a bijection that's an isomorphism, we would run into issues, because I need to, since V4 and V5 are adjacent, they're both degree 2 and they're adjacent in this graph, then whatever I map them to is going to have to be adjacent in the second graph. And I have no way of taking a degree 2 vertex in the V graph or in this right-hand graph, and mapping it to a degree 2 vertex that's adjacent to another degree 2 vertex in the first graph. So that sort of adjacency, again, would need to be preserved, and I can't do that with the second one. So that is finally enough to tell us that these are non-isomorphic. Next, we're going to look at adjacency matrices. The adjacency matrix of a simple graph with n vertices is a 0, 1 matrix where the ijth entry is 1, if and only if the vertices v sub I and v sub j are adjacent. So to look at an example, let's maybe pull one of the ones from up here. Look at the first one that we had over there. Let's get that copied in here. And because we have 8 vertices, we're going to have an 8 by 8 matrix. There are going to be quite a few zeros in this because we don't have a lot of connections. But we'll go ahead and draw that rather large matrix. Use brackets for the delimiters since it's on the big side here. And then we'll just list out, label our rows and columns. Because of the subscripting here, it's probably clear that we would just go in order of increasing subscripts, just in case. If we have something where there might be more ambiguity, then you can list them out like this to label the rows and columns. So if I'm looking at, say, U1, it's not adjacent to itself, so I'm going to have a 0 there. U1 and U2 are adjacent, so we're going to put a 1 there. And if you have a directed graph, then it's possible that you could have a 1 in a certain position that's not mirrored on the other side of the main diagonal of this matrix, going from upper left to bottom right. But in this case, because it's undirected, I'm always going to have the symmetric mirrored 1 on the other side. So in this case, U2 and U1 are adjacent, U1 and U2 are adjacent. So the 1 here, I'm also going to get a 1 down here. So we're going to have that symmetry between the two. U2 is not related to itself, so I'd have a 0 in that second entry there. U1 is not adjacent to anything else, so I'm just going to have zeros for the rest of that particular row. And then U2 is, again, adjacent to U1 and also, or adjacent with, I guess would be the proper term since it's not direct, adjacent with U1 and U3. So I'm going to get a 1 there. But then again, U3 and U2 are adjacent, so I'm also going to have that symmetric reflected pair on the other side there. U3 is not adjacent with itself, so we get a 0 there. U3 is also adjacent with U4, so as we were to continue along here, we'd get a 1 there, and it's also adjacent with U5, so we put a 1 there. Again, those are going to get mirrored down here. So U4 and U3, U5 and U3, we're going to get 1s there to mirror, again, the ones that we have over here. We're going to continue with, this one would have 0s everywhere else along there, and so on. Same thing with our U2. So we're going to get 0s. And then U5, we've already got the U3 entry marked off, and then that is also adjacent with U6. So that's going to give us another 1 way over here. And then U6 and U5 are going to be adjacent as well. So again, with this, we're always going to, because we don't have the loops, we're going to get 0s on all of the diagonal entries here. That one should be moved down a little bit more. Aren't quite lining up. That's okay. And then continue with that, let's see, the U6 and 7 are adjacent, so 6 and 7 right there, and then 6 and 7 down here. Again, we're going to get that mirroring, and then 6 and 8. It's going to give us a 1 over here, and then the 8 and 6, we're going to get a 1 over there. Again, kind of a big matrix because we had 8 vertices, but again, just filling in a 1 if those two vertices are adjacent with each other, and otherwise we'll put in a 0. The next theorem that we'll look at is the handshaking theorem. In any undirected graph with m edges, the sum of the degrees, so if I add up all of the degrees for all of the vertices in my graph, then we're going to end up with 2 times the number of edges. Let's look back at one of our undirected graphs. Maybe we'll just use this one as an example. Copy that in here again, since we've already got it ready. This is undirected, and if we look at the number of edges, we've got 1, 2, 3, 4, 5, 6, 7 edges. Is equals 7. And if we take the sum of all of the degrees, it's going to be equal to, just write this out as we go. So I've got 1 plus, I'll just go through in the index order. So U1 has degree 1, U2 degree 2, U3 degree 3, U4 has degree 1, U5 has degree 2, U6 is degree 3, U7 is degree 1, and U8 is degree 1. And if we add all of those up, so we'll get 1 plus 2 is 3, plus 3 is 6, plus 1 is 7, plus 2 is 9, plus 3 is 12, plus 1 gives us 14, which is 2 times 7. So the handshaking theorem, at least for this one, does work out. And if we think about what's happening there, if we have an undirected graph, every time we add an edge, so think about maybe just starting with all of the vertices but none of the edges filled in, as we add in edges, then each edge is going to be incident with 2 different vertices. So it's going to add 1 to the degree of each of those 2 vertices. So if I'm adding up the total degrees, then it's going to add 2 each time we add an edge. And you could go through and formalize that idea and use induction to show that this would generalize. But that would be the basic idea, is that as you increase the number of edges, then you're going to end up with 2 more in the degree. And a corollary to that says that in any graph, we're going to have an even number of vertices of odd degree, because we're ending up with an even result here. So the sum of the degrees is always even, which means that I can't have an odd number of odd degree vertices. Otherwise, then the sum would end up being odd instead of even. So those facts can be useful as we're trying to look at more general proofs or properties involving graphs. We know that the degrees and the number of edges are related in this way, and we know that we can't have just any degrees that we want. We have at least some restrictions, just based on what we've got so far, on what those quantities are going to need to look like.